In our previous lectures, we have defined the problems of interpolation and approximation and derived various methods for constructing the interpolating polynomials. We shall discuss now the application of interpolating polynomials in other areas. In particular, we can apply them in the numerical differentiation and numerical integration areas. Let us now first of all discuss the what we mean by numerical differentiation. So, let us define numerical differentiation. We are given a data of n plus 1 points which we were considering earlier. So, we have this data x f x, x 0 f at x 0, x 1 f at x 1 and so on x n f at x n. So, we have a data of n plus 1 points. We wish to find the derivative or higher order derivatives of the function f x which represent this particular data, either at a nodal point, that is x 0, x 2, x n, or at a non nodal points somewhere in between these data points. So, for any point x contained in x naught to x n, we would like to find out a derivative or higher order derivatives for the solution of this particular problem. There are three approaches for finding the numerical differentiation methods. The three approaches are as follows. The first approach uses the interpolating polynomials, that is, we shall call this as methods based on interpolation, based on interpolation. In these methods, what we do, given a data, we construct the Lagrange interpolating polynomial or other forms of the interpolating polynomial and then differentiate it required number of times to find the derivatives at the nodal or non nodal points. We can also find out the error estimate in the derivatives also. The second method is methods based on difference operators, methods based on difference operators. Now, when the data is equispaced, then we have defined the forward difference, backward difference, central difference. Now, when the data therefore is equispaced, we can use these difference operators to either construct the interpolating polynomial or directly obtain the value of the derivative at a required point. Therefore, this will be a simplification of what we have done in the first step, that is, here we are using the data which may be equispaced or which may not be equispaced. So, this is general data that is given to us. And the third one is methods based on undetermined coefficients, undetermined coefficients. Now, in this case what we do is we write down a formula which we want, a particular type of formula depending on the application. We construct a formula which contains the ordinates that is given, the ordinates that is given to us, abscissa given to us and some parameters in that. These are arbitrary parameters. We use the Taylor series expansion of this part in the for all these terms, simplify them, compare the coefficients of the powers of h, write down the required number of equations as the number of parameters, solve them. If you can solve them, the method which you have written exists, otherwise it does not exist, and the next non vanishing term would be the error in that particular formula. All these three methods give the similar type of methods, and let us discuss each one of them and see how we can obtain the methods for numerical differentiation. So, the first one we shall take will be methods based on interpolation. Now, we are given this data, that is given to us x I, f I is equal to 0, 1 to n. What we shall say, construct the interpolating polynomial, construct the interpolating polynomial. Now, it is our convenience which particular polynomial you are trying to construct, a Lagrange interpolating polynomial or a divide difference polynomial or any other polynomial. If it is equispaced, we can go to Newton forward backward. So, in general we are writing an interpolating polynomial Pnx. That means f x is now approximated by Pnx. Now, I can differentiate it and get f dash x is equal to approximately Pn dash of x. So, in general I can differentiate it r times to get the Pn r x. So, I can differentiate it and get the value of the derivative either at the nodal point, that is xi, or at non nodal points. Then we define the error also as E, again superfix will put r to define the order of the derivative that we are taking, and that will be equal to f r x minus Pn r of x. Now, before we actually write down the numerical differentiation formulas, a word of caution should be given for the numerical differentiation. And what that is, there are in fact two points that have been noted. That is, when a data is given to us, we really do not know what the function f x is actually representing. In other words, does the derivative of the function which represent that function exist at all, or even if a first derivative exists, does higher order derivatives exist at all. Therefore, we really do not know whether the derivatives of a particular function that is representing data is existing, and maybe we are trying to find out the derivative which does not exist. Therefore, in that case numerical instability would arise. And for example, if you take y x is equal to root x, now let us write down the data artificially starting at x is equal to 0 to some x is equal to 5. Now, at x is equal to 0 it is well defined. So, I have got a value 0, at 0 0 I can construct an interpolating polynomial. Suppose you are trying to find the derivative at x is equal to 0. Now, derivative dy by dx is 1 upon 2 root x. Now, at x is equal to 0 derivative does not exist. Therefore, we will be landing into serious numerical instabilities if you are trying to construct or find out the derivative at a point where the derivative may not exist. Therefore, numerical differentiation must be done with great care. And the second observation that should be made is numerical differentiation is very sensitive to round off errors, which we are going to show and also see how badly the numerical differentiation will affect the solution. If suppose you have taken a data of say 6 place accuracy data or a 4 place accuracy data, how many places can you expect in a numerical differentiation? Now, therefore, we were going to show that particular aspect of it. The numerical differentiation is very sensitive to round off errors. So, these are the 2 points that you must note for the numerical differentiation. Later on we discuss, when you discuss numerical integration, the problem it becomes just the opposite, it is always a stable process, whereas the differentiation can be an unstable process. Now, with this caution, let us now construct the methods based on interpolation. So, let us first start with non-uniform points. Non-uniform points. Therefore, we can straight away construct the Lagrange interpolating polynomial that fits this data. So, let us take the Lagrange interpolating polynomial. And that is, we are writing P n x is equal to summation of k is equal to 0 to n L k x f of x k, where L k x are our Lagrange fundamental polynomials. Let us write down what is our L k of x. I shall now use a slightly different notation that I used earlier, and I will tell you the reason. I will denote this w x that we were using earlier by pi x. This is x minus x naught pi dash of x k. Now, our pi of x is now the product of all these factors x minus x naught, x minus x n. We shall reserve this w x that we were using earlier for the weight function that is going to come in the numerical integration. We have also proved that the error of interpolation is E n x is f x minus p n x, and this is equal to the product of all these factors, that is pi x divided by n plus 1 factorial f n plus 1 of some xi, where xi lies between the first and the last points, that is x naught less than xi power of n. Now, what we have stated is that if I want the derivative now, take this particular polynomial 1 and then just differentiate it. So, I can now differentiate it and write p n prime of x is equal to summation k is equal to 0 to n. I have to differentiate L k. So, differentiate it with respect to x f x k. Then correspondingly I can look at what happens to the error also. So, I can differentiate this error also. So, I will then have E n dash of x is equal to 1 upon n plus 1 factorial. Now, we should remember that xi is a variable quantity, is an unknown quantity lying between x naught to x n. Now, the value of xi is going to change as we change your value of x, therefore, that will be taken as a variable. Therefore, we shall have this as d upon dx of pi x into f n plus 1 x plus the second term, that is pi of x d upon dx of f n plus 1 of xi. So, I will take this as product of two functions and then differentiate it as a product. So, derivative of the first one into this plus pi x into derivative of this. Now, in the case when we are trying to find out the derivative at a non nodal point, that is not x naught, x 1, x 2, x n, then we do not know this particular quantity. Therefore, we will not be able to go exactly what will be the error at a non nodal point, but at a nodal point it is easy for us because pi x in that case is 0 at a nodal point, because there is a product of these factors. So, if I take x is equal to any one of the nodal points, then pi x is equal to 0. Therefore, at the nodal points I can give the exact expression for this. So, let us write down at a nodal point. At a nodal point, say x k, pi of x k is equal to 0. Therefore, our derivative at this point x k is 1 upon n plus 1 factorial d upon dx pi x evaluated at x k f n plus 1, I think this xi, this is xi. Therefore, I will be able to write down the bound of this immediately. I can take the magnitude on both sides and write down what will be the bound of this error from this. That will be 1 upon n plus 1. Now, this is a number because this has been differentiated and evaluated at x k also. So, this is only a number. So, this is d upon dx of pi x evaluated x k, and this we will write it as m n plus 1. M n plus 1 is the maximum of this, where m n plus 1 is the maximum of in the interval x naught x x n magnitude of f n plus 1 of x. So, I can write down the expression for the derivative of the error at a nodal point much more easily. As I said, if it is not a nodal point, then there will be contribution from the second term also, and we do not know how this particular quantity can be bounded. Now, let us take a particular case from here. Let us just look at some of the cases. Let us start with linear interpolation. Now if I want the higher order derivatives, I just have to go ahead and then differentiate it further. So I can differentiate it r times, and I can have here it differentiate it r times. So if I want the, for example in the general case, if I want the rth derivative, I can just differentiate the expression that we have written earlier, that is L k differentiated r times of x f x k, and correspondingly I can get the expression for the derivative also, the second derivative, a third derivative. Again you will see that the contribution, now I will have to differentiate this further. So when I differentiate it further, there will be more number of terms that will be available, and at a nodal point we are happy because we can able to get the bound. At a non nodal points also again it will be difficult for us to write down what will be exactly the error. Now let us start with linear interpolation. So we have got only 2 points which we are considering, x naught f naught and x 1 f 1. These are the only 2 points, and the Lagrange interpolating polynomial is p 1 x is equal to L 0 x f of x 0 plus L 1 x f of x 1. There are only 2 points, so let us write down our interpolating polynomial x minus x 1 by x naught minus x 1 f x naught. This is x minus x naught by x 1 minus x naught f of x 1. So this is the linear interpolation Lagrange interpolating polynomial, which we have opened it up for L 0 x and L 1 x, retain it in the suitable form. Now let us differentiate it. So if I differentiate it, p 1 prime of x is equal to derivative of this is 1 upon x naught minus x 1 f x naught, derivative of this is 1 upon x 1 minus x naught f of x 1, which I can write it as, I can take x 1 minus x naught common. So I can write down f of x 1 first, and this with an opposite sign x naught divided by x 1 minus x naught. Which of course is a constant, because we started with a linear polynomial degree 1. So we have differentiated it, therefore you will get a constant. Now what that this imply? It implies that the slope is the same at both the points. If you evaluate it at x naught, it will be the same, if you evaluate at x 1 it is the same. So that means p 1 dash at x naught, p 1 dash at x 1 are same, slopes at both these points are the same, and it is given by this particular value. I mean that is to be expected, as I mentioned, because we are taking a linear interpolating polynomial degree 1 and differentiated it, therefore we are getting constant. It is constant at all points x naught x 1 and also at any point in between also. Slope will be a constant across x naught to x 1. Now let us look at the error. Now error E 1 is x minus x naught x minus x 1 divided by factorial 2 f double dash of xi, x naught less than xi less than x 1. Now let us differentiate it. So I will have E 1 dash is equal to 1 upon factorial 2, whatever we explained here, let us repeat this one. So I am differentiating this as a product. Now this is x squared minus x naught plus x 1 into x plus x naught x 1. So let us differentiate it, 2x minus x naught plus x 1, that is the derivative of this, into f double dash of xi plus x minus x naught x minus x 1 d upon dx of f double dash of xi. Now what we were mentioning earlier is that this quantity is a quantity which is completely unknown for us. I will be able to find out the error much more easily at the nodal point. That means the value of the error in the derivative at the point x naught, that will be 1 upon factorial 2. I substitute x is equal to x naught here. So, I will get here x naught minus x 1 f double dash of xi at x naught, this is equal to 0. So, I am able to write this particular quantity. So, that I can write down the bound for this as a derivative E 1 dash x naught magnitude is less than x naught minus x 1 in magnitude divided by 2 m 2, where m 2 is our usual notation, that is the maximum of f double dash of x in the interval x naught to x 1. Now, I can find out what is the error at the other point x 1. Now, if I substitute x is equal to x 1 here, I will get 2 x 1 minus x naught minus x 1. So, x 1 minus x naught. So, I will have 1 upon factorial 2 x 1 minus x naught f double dash of xi. Again the second term vanishes at x is equal to x 1. Now, this error is same as this error except it is of opposite sign. So, this is here x naught minus x 1, this is x 1 minus x naught, therefore, the slope of error is of opposite sign, but its magnitude is the same. So, the magnitude of this is less than or equal to x 1 minus x naught. We need not write magnitude because x 1 is greater than x naught, we can actually write as x 1 minus x naught into m 2. Therefore, it is possible for us to find out what is exactly the error. Now, I can go ahead and then get the any derivative, second derivative, third derivative. Only thing is I will have to increase the order of interpolating polynomial to second order, third order, fourth order, so that I can find the first derivative, second derivative, third derivative and so on. Let us just restrict up to quadratic interpolation. So, let us take what is quadratic interpolation. So, we need to write the Lagrange polynomial L0 x f 0 L1 x f 1 plus L2 x f 2. Now, if I want the derivative, I will just write down p 2 prime x derivative of L0 x f 0 plus derivative of L1 x f 1 plus derivative of L2 x into f 2. Now, this is a quadratic polynomial. So, I can differentiate it once more and get the second derivative also. So, I can also write down what will be the second derivative in this case, that is L0 second derivative f 0, L1 second derivative into f 1 plus L2 second derivative into f 2. Now, what I do is I write down all these polynomials L0, L1, L2, differentiate it number of times that is required, substitute it and then evaluate whatever the point that we want. For example, let us derive one particular formula, the others you can, it is a trivial, you can get it. So, let us try to get what will be the value of p 2 prime at x naught. So, let us try to get what is the value of this at one of the nodal points. This will be, I substitute x is equal to x naught, therefore, L0 prime x 0 f 0, L1 prime at x 0 f 1, L2 prime x 0 f 2. Now, let us write down the expressions for L0 x. The expression for L0 x is equal to x minus except x naught, that is x naught x 1, x minus x 2 by x 0 minus x 1, x 0 minus x 2. Let us write down the what is the expression for the numerator. The numerator is x squared minus x 1 plus x 2 into x plus x 1 x 2. So, that is our numerator. Therefore, I will get the derivative of this as I differentiate this 2x minus x 1 plus x 2 divided by the same quantity x naught minus x 1 x naught minus x 2. Now, I can substitute x 0 here and then evaluate what is our the first term that is required for us, that is your L 0 dash x 0. So, I can substitute here L 0 dash x 0, that is equal to 2 times x 0 minus x 1 plus x 2 divided by the same quantity x naught minus x 1 x naught minus x 2. If I want the derivative at some other point x 1 x 2, yes, I would now use that particular quantity here, and if it is not a nodal point, then I will take that particular value of x is equal to some eta. So, it will be 2 eta minus x 1 minus x 2 divided by this quantity. Now, let us write down L 1 x. L 1 x is x minus x naught x minus x 2 divided by x 1 minus x naught x 1 minus x 2. Now, the numerator is, let us multiply it out, x squared minus x naught plus x 2 x plus x naught x 2. This is our numerator. Now, let us differentiate this. L 1 prime of x is equal to 2 x minus x naught plus x 2 divided by x 1 minus x naught into x 1 minus x 2. Again, it can be evaluated at any nodal or non-nodal point. Now, I need this derivative at x 0. So, I substitute it. Now, here this is 2 x naught minus x naught. So, I will have only x naught here minus x 2 divided by x 1 minus x naught into x 1 minus x 2. Now, similarly, let us get the third quantity, that is L 2 of x. L 2 of x will be x minus x naught into x minus x 1 divided by x 2 minus x naught x 2 minus x 1. Now, let us write the numerator. The numerator is x squared x naught plus x 1 x plus x naught x 1. Therefore, I can find the derivative. L 2 dash x is derivative of this, that is 2 x minus x naught plus x 1, and the denominator is x 2 minus x naught x 2 minus x 1. Therefore, again I can evaluate this at any nodal point or non-nodal point. I get 2 x naught again minus x naught, that is your x naught minus x 1 by x 2 minus x naught x 2 minus x 1. Now, all the quantities have been evaluated. So, we go back and substituted here the values of L 0 dash x naught, L 1 dash x naught, L 2 dash x naught, f naught, f 1, f 2 are given to us as the ordinates in the data, substitute it and we evaluate it and find the value of that particular expression. So, we can get the value at any nodal point or non-nodal point straight away using your Lagrange interpolation. However, all these derivations get simplified if you are using the uniform space data, that is your equi-space data. So, let us see what is the simplification for equi-space data. Therefore, the step length xi minus xi minus 1, let us take it as h. Now, in this case we can use the formula Lagrange interpolation, or since it is equi-spaced we can use the Newton's forward backward difference formulas, which we will take it in a moment, but let us now first concentrate on how we can simplify what we have done already earlier. So, let us start with what we have written here earlier, the formula for the first derivative, the formula for the first derivative using the Lagrange interpolation is this. Now denominator is x1 minus x naught, that is simply equal to h. Therefore I can straight away write down, if I take p1 dash x, that is we are discussing the linear interpolation. Then p1 dash x is equal to 1 upon h of f1 minus f naught. This is f1, this is f naught, and this is only step length h over here. And also let us write down what is our E1. So we have the expression for E1 dash at x naught, that is equal to half x naught minus x1, this is minus h, x naught minus 1 minus h. Therefore the error at x naught will be equal to minus h upon 2 f double dash of xi. Whereas the error at x1 is x1 minus x naught by factorial 2. So we will have here h upon 2. So this is the error at x1 is plus h by 2 f double dash of xi. Now we therefore the error is of opposite sign, they are of same magnitude, and we shall call these as the order of the formula is error is h to the power of p is equal to 1. Therefore these are all the first order formulas. So these are called the first order formulas, that is we are talking of order of h to the power of p as the error, and here in this case p is equal to 1. Therefore we are calling them as a first order formulas. Now let us take quadratic interpolation. Now for deriving the quadratic interpolation I will not use the Lagrange, because we have the much more simple formula, Newton's forward backward difference formula. Let us use one of them for this. So let us take the 3 points, here is x naught f naught, x1 f1 and x2 f2. Let us take these 3 as the points. Since these are only 3 points, only second order forward difference or second order backward difference exist. So therefore our Newton's formula will be, let us take the Newton's forward difference formula, Newton's forward difference formula, that is f(x) is equal to approximately f of 0. I will use that we have derived formula in terms of u. So I will write down that formula, u into this 1 upon factorial 2 u into u minus 1 delta squared f naught. If you remember, we have defined u is equal to x minus x naught divided by h, and the error expression for this is the next coefficient, binomial coefficient, that is u minus 1 u minus 2 divided by factorial 3 h cubed f triple dashed of xi. Xi lying between the first and the last points, x naught less than xi less than x2. Now we mentioned earlier that for computational purposes this formula would be useful, because u is a small number and these binomial coefficients would reducing very fast as we go along. Therefore if you write down the forward differences and write the polynomial interest of this, these later terms are going to be very small numbers. It is as if you are adding some correction terms to these previous terms and then getting a finer value. Now let us write down what is our derivative. I want f dash x. The variable is u, therefore I will write this as df upon du into du by dx, df upon du into du by dx. Now du by dx, let us first write it, du by dx is 1 upon h, u is equal to x minus x naught by h, du by dx is 1 over h. So this is 1 over h. Now we differentiate this with respect to u, therefore differentiate it, I will get delta f naught, this is u square minus u, so differentiate it, 2u minus 1 delta squared f naught. So, let us number this as 2. Therefore, we have the expression for the derivative very simple. We have one first forward difference, second forward difference. If I want at any nodal point, I will take the nodal point. If it is a non-nodal point, then u has got a different value. I can substitute that value and find the derivative at any nodal or non-nodal point from here. Now, let us write down what will be the error in this case. Before write the error, let us write down let us just look at how this formula looks like at a nodal point. Let us take x is equal to x naught. How does it look like? Then derivative at x naught will be now when x is equal to x naught, the value of u is 0. When x is equal to x naught, value of u is equal to 0. So, we will have u is equal to 0. Therefore, this is 1 upon h. I am substituting u is equal to 0 in this. So, this is delta f naught, that is minus half delta squared f naught. Now, let us simplify this, that is equal to, let us take 2 outside. So, 1 upon 2 h, 2 times delta f naught is f 1 minus f naught, delta squared f naught is f 2 minus 2 f 1 plus f naught. This is the second forward difference. This is equal to 1 upon 2 h. There is minus 2 f naught here and a minus f naught here. I have minus 3 times f naught. I have a plus 2 f 1 here and a plus 2 f 1 here. So, I have 4 times f 1, then I have minus f 2. So, this is the formula that I have for the derivative at x naught. Now, notice whether you are writing it correctly or not, the sum of the coefficients have to be 0. This is 4, 3 minus 1, sum of the coefficients is going to be 0. Now, let us write down what is the error expression for this. Now, I will take this error expression and differentiate it. So, I can differentiate e prime of x is equal to again dE upon du into du by dx. Now, du by dx is again equal to 1 upon h. So, I will retain this over here and then differentiate it. We have a factorial through. So, let us put our 6 also outside. Then I will have here d upon du of the derivative of this u minus 1 u minus 2 into f triple dash xi plus u into u minus 1 u minus 2 d upon du of f triple dash of xi. Now, this is the general expression for all the cases for all the derivatives. Now, let us get what is the value at x naught. So, I will have derivative at x naught, error derivative at x naught is 1 upon 6 h. Now, at x naught u is equal to 0. So, this is going to be 0, second expression is going to be 0. So, let us differentiate this. This is your product u into u squared minus 3 u plus u, this is your plus 2. So, that is your u cubed minus 3 u squared plus 2 u. I differentiate it and then put u is equal to 0. So, if I differentiate it, I will get 3 u squared minus 6 u plus 2. So, let us write down one or maybe one more term we can write down. This is equal to d upon du u minus 2 u squared plus 2 u into f triple dash of xi, evaluated at u is equal to 0. Therefore, I get here only 2 by 6, that is 3, 1 upon 3 h. Where is our, I should put h cubed also here. We have a we have a h cubed also here. So, I write it outside h cubed, write it h cubed and h cubed into f triple dash of xi. Therefore, this is equal to h squared by 3 f double dash of xi. Therefore, the magnitude less than or equal to h square by 3 m 3, where we have written m 3 as maximum of f triple dash of x in the given interval x naught to x 2. Now, you can see error is of the order of h to the power of p is equal to 2. Therefore, we have p is equal to 2. Therefore, this is a second order formula that we have obtained. This is a second order formula. Now, it is interesting to see how the same formula would behave at different points. So, let us take this formula at x is equal to x 1. Let us take now at x is equal to x 1, that is the middle point. There are 3 points we have taken x naught f naught, x 1 f 1, x 2 f 2. So, the middle point at x 1, the value of u is x 1 minus x naught divided by h. X 1 minus x naught is h, therefore, h upon h is 1. Therefore, in this case u is equal to 1. At x is equal to x 1, u is equal to 1. Now, let us substitute what will be the value of f prime. So, let us put it this way. So, therefore, f prime at x 1 is 1 upon h delta f naught. Now, at u is equal to 1, this gives you plus 1. So, I will have plus half delta squared f naught. And let us again open this up, 1 upon 2 h, 2 times f 1 minus f naught plus f 2 minus 2 f 1 plus f 0. This is 1 upon 2 h, this is minus 2 f naught plus f naught. So, minus f naught, and this is 2 f 1 minus 2 f 1, it cancels. So, I will have here f 2, or simply I will rewrite it in first f 2 and this f naught. Therefore, the formula is simple, it is symmetrically placed about x 1, that is this is f at x 2, this is x 1, this is f at x 2 minus f x 1. That means, we are really looking at a central difference formula corresponding to a central difference formula. This is f at x naught, f at x 1. The step length is h, therefore, x 2 is 1 step h ahead, x 0 is 1 step behind, therefore, this is symmetrically placed approximation. Now, let us see how the behavior of the error would be at this particular point. And for writing the error expression, I just need to substitute here u is equal to 1, because the same expression we have got at u is equal to 1. Therefore, this will be 1 upon 6 h into we can substitute it over here. This is equal to derivative of this is 3 u squared minus 6 u plus 2 evaluated at u is equal to 1 f triple dash of xi into h cubed. And this gives us minus 1, this is at u is equal to 1, this 5 minus 6, that is minus 1. So, I will have minus h square by 6 f triple dash of xi. So, the error is minus h square by 6 f triple dash xi. So, that the bound is less than or equal to h square by 6 m 3. Now, you can see that the error in the previous case was h square by 3 and now we have h square by 6 which is reduced by a factor of 2, and that should be expected. This formula turned out to be a central difference approximation, that is we have got symmetrically placed points, so that if you Taylor expand this, the odd derivatives would cancel. And similarly if I take the third formula x is equal to x 2, then when x is equal to x 2, if I go back and substitute x 2 here, x 2 minus x naught is 2 times h, divide by h, u is equal to 2. So I will then have u is equal to 2 in this case. Now then I can substitute it straight away in this. So let us substitute u is equal to 2 in this. So we will have here f prime at x 2 is 1 upon h delta f naught plus this is 4 minus 1, that is 3 by 2 delta squared f naught. Let us simplify this, 1 upon 2 h twice f 1 minus f naught plus 3 times f 2 minus 2 f 1 plus f naught, that is 1 upon 2 h, this is minus 2 f naught and plus 3 f naught. So, I will have f naught, this is plus 2 f 1, this is minus 6 f 1. So, I will have minus 4 f 1 and plus 3 times f 2, plus 3 times f 2. Now, interestingly if you look at the formula at the two end points, we are taking quadratic only interpolation x naught x 1 x 2. At x naught this is of the sign minus 3 minus 1 and 4, and if you go to the other point, the the roles of this is reversed with an opposite sign. So, this becomes f 0 with a negative sign throughout, and the roles of the first and last ordinates gets interchanged, this is f naught and f 2. So, this is how it comes, the first and last points, the interpolation at this. Now, I leave this as an exercise to you, can just find out derivative at x 2 is again equal to h square by 3 f double dash of xi. It is the same as at the first point it would be. Now, if we want the second derivative would be possible because we are doing the quadratic interpolation. So, I can find out my second derivative also f double dash of x, that will be by definition d upon dx of f dash x. Now, I need to use this to get the next derivative. So, this will be d upon du of the expression that we obtained for f dash x into du by dx. Now, du by dx is 1 upon h, there is already a 1 upon h here. So, I will have 1 upon h square. Now, I am differentiating with respect to u, therefore, I will get here 1. So, simply I will get delta squared f naught. Therefore, it is only the second forward difference divided by h square. In fact, earlier when we have gave the relationship between the derivatives and the forward differences, this one we have got it there also. So, this is the expression for f double dash, that is simply equal to 1 upon h squared of f 2 minus 2 f 1 plus f naught. Obviously, this is a constant because we have taken a quadratic polynomial, differentiated 2 times, and therefore, we will get a constant. Therefore, second derivative at all the 3 points, in fact at every point in the interval are the same, they are all the same. Okay, we will stop at this today, we will take an example for this next time.